So the graph of secant, let's look at graph of secant or cosecant functions. But first of all, graph of secant. And secant can be written as reciprocal of cosine x, as long as cosine x is not 0. Because when cosine x is 0, reciprocal is not possible, right? It's undefined. So we know that whenever cosine x is 0, the secant function has no value, undefined. So we must exclude those x's where cosine x is 0. So but when cosine x is is getting smaller and smaller, then the reciprocal will be larger and larger. So we can imagine some relationship between the graphs of secant and cosine x. So let's see the one period of cosine function. So in this picture, if we look at the cosine, which is showing it's certainly a continuous curve, right? This cosine curve. So it's the basic cosine curve, its amplitude is between 1 and -1. So here the largest value is 1, the smallest is -1, and sometimes it's 0 because you have infinite number of x-intercepts. But whenever cosine is 0 and secant is undefined, so that's why we have those vertical lines to make sure that we have no secant value at each one of those zeros of cosine. So whenever cosine function is 0 and secant is undefined. And let's also look at when cosine is 1, secant is also 1. So that's a point. They both the cosine function and secant function will pass. That means they have the same function value. Because when cosine is -1, the secant reciprocal of -1 is also -1. So this is a -1 here. And secant function also. So 1 or -1, the reciprocal will be the same. So those values, they pass the same point. But then let's just look at only one period of the cosine function. You see when cosine from 0 to 2 pi, and cosine is getting smaller and smaller, when it's close to 0 but not equal to 0, what happens? And when this denominator is getting smaller and smaller, and the fraction, right, which is a secant value of x, so the fraction is getting bigger and bigger. So then we notice an increasing curve. So we notice this, that shows the reciprocal of cosine is increasing when cosine is approaching 0. But when cosine getting sufficiently close to 0, then this secant function will be increased without bound. And when the cosine is equal to 0, then that vertical line becomes a vertical asymptote. That means we have a vertical asymptote where the cosine is 0. And here is another. So then the secant, we continue to examine when x, what if x is bigger than half of pi? When x is less than half of pi, we notice the cosine function is positive, right? All these are positive, approaching 0. So the reciprocal will be positive, approaching larger and larger values without bound. So it's going to increase. But when the cosine value takes negative values, and the reciprocal of a negative number is also negative. So we remember this identity, the secant x, when this is a negative, the denominator is negative, the reciprocal is also negative. So, and we see, especially when cosine x is approaching 0, and this is going to be more and more negative. So when we see this in this trend, so when the cosine x are getting more and more closer to 0, actually the secant function will be approaching negative infinity. Yeah, for the similar reason, the other side, you see the cosine function also negative. And when cosine function is getting closer and closer to 0, and the reciprocal of that quantity is negative and more negative, it approaches negative infinity. Yeah, so all because of that identity. And then when cosine x is actually equal to 0, when cosine x is equal to 0, then secant function is undefined. So we have a vertical asymptote here, x equals 3 pi over 2. So this is another vertical asymptote where secant function is undefined. So this picture shows we just draw the basic cosine function. Then we use the graph of cosine to sketch graph of secant function. So we see this. Okay, let's use the red color to show. Okay, from 0 to 2 pi, right? So we can see this is and we have a number of vertical asymptotes whenever cosine is 0. So, and from when the cosine is positive, then the reciprocal of cosine, which is secant function, is positive. And yeah, so we get from 0 to 2 pi interval, we have 1 period of the secant function. But when you look at extension, for example, from negative 2 pi to 0, to this 0, then we can get another period of secant function. So this pattern will repeat. So let's draw another period. So this is that. And then just this. Yeah, so we see 2 periods, and then you can extend this graph and then to see more periods. Okay, once we have the secant, Then similarly, we can sketch cosecant. So cosecant function is the reciprocal of sine function. So that's why when the sine function is zero, the cosecant is undefined. So here is the okay, so let's so let's try to get out of this. And let's write our cosecant function. Cosecant x is a reciprocal of sine x. That's a reciprocal identity, right? So of course, cosecant function is defined only if the sine function is not zero. That means with sine function is zero, then the cosecant is undefined because you're dividing zero or 1/0. So they are reciprocal to each other. So whenever one is zero, the other is undefined. So let's look at sine function. The sine function here, whenever sine function is zero, you see at any multiple of pi, the sine function will be zero. So that's where cosecant function is undefined. Yeah. So that's we just see those are the values. Those are the places we don't have a value for cosecant x. Okay, now why they're vertical asymptotes? Because let's pick one period of sine. So just try to see one period of sine. Let's see from 0 to 2 pi, right? Let's easily pick from 0 to 2 pi, this interval. This is the interval, one period of sine function. The sine function is here, you see increasing and then decreasing all the way to -1 and then increasing to 0. So that is one period of sine function. And then we want to see when the sine function is 1, of course, reciprocal is also 1. So when sine function is 1, both sine function and cosecant, the functions, yeah, both two functions will have the 1 because 1 has reciprocal 1. And when the sine function is -1, reciprocal is also -1. That means cosecant is also -1. So they must pass the same point. So that's those are the common points shared by both sine and cosecant. And what if when sine is not 1 or -1? When sine is, let's see, when sine is less than 1, right, getting smaller and smaller, what happens to the reciprocal of the sine? So when sine is less than 1, the reciprocal is bigger than 1. So let's see the behavior is the reciprocal will be larger than 1. And also, it's clear that when the sine value is very, very close to 0, not equal to 0, when it's approaching 0, what's the behavior of the reciprocal? So you see the denominator is getting smaller and smaller and can be infinitely small. The reciprocal will be infinitely big. So we can predict that the reciprocal, which is the cosecant function, will be sufficiently big. It's going to increase without bound. So that means this x equals 0, the vertical line or y-axis, right? It's a vertical asymptote to the cosecant x. And let's think the other way. So when sine x is a positive, but getting closer and closer to 0, so if we're going this direction, and reciprocal is also getting larger and larger. The reciprocal function, which is the cosecant function, is going to increase, becoming larger and larger. But when x is pi, well, this curve will never intersect with this x equals pi because x should never be equal to pi. Our cosecant x function is undefined at this point. So cosecant curve will never intersect with this, and those vertical lines are just vertical asymptotes to show the some kind of framework for the cosecant curve. Okay, similarly, we can see at -1, right? The cosecant function is also -1, but when the sine function is negative, it's becoming approaching 0. The reciprocal is also negative and becoming more and more negative. So similarly, when the sine function is negative, coming to 0, then the reciprocal of that quantity is becoming more and more negative. So we have this. So you can see this is the one period, and all those vertical asymptotes when x is 0, pi, 2 pi, 3 pi, etc. So here is graph of one period. The red curve is one period of cosecant function. And in order to draw the one period of cosecant function, we made use of the sine function. So to get the sketch of cosecant. And now if you, okay, so fix that. And now if you want to do some variations of cosecant function, so let's look at, for example, 3 secant half of x, or something cosecant. So it doesn't matter which one. So let's just let's look at one function. This example, it is -3 cosecant 2x. And we can first decide the period. The period of this function is pi, right? Using the formula, because the cosecant function has the basic function, if this is a one variable cosecant t, if that has a period of 2 pi, and we know this given function will have a period pi, because 2 pi over 2 get pi. And then we want to sketch some points. For example, For the sine function, we can quickly use 5 key points, right? When this, let's call it the t, for example, this is the sine of t. Let's just do a change of variable, right? Just look at the basic function sine of t. When t is taking each one of those 5 values, we get corresponding y values. Yeah. So now we get 5 key points. But of course, we don't want to plot t versus y. We want to plot x versus y. What are the corresponding x? So we know this is just the 5 key points method for the sketch of a sine function, right? So we can quickly get, yeah, if t is that, t is twice of x, so x must be half of the corresponding t value. You see, half of this. So this, when t is pi, then x is half of pi. So then when t is 2 pi, then x is half of 2 pi. So we get the x. So for each x, we get a y value. For each x, we get a y value, right? We get 5 points. So this is a quick review of the sine, one period of sine curve, how to quickly sketch it using 5 key points. So let's get that first. So then after we get that, then how do I get this curve? Because right now with the 5 key points, I get -3 sine 2x, which is not the given function. You see, the sine is actually reciprocal of the cosecant. Yeah, that's not the function we need to graph. So how do I get from the -3 sine 2x to graph of this function? So let's use our technique first. We show the -3 sine x. Okay, so sine 2x. Okay, so let's see. Where is the sine function? The curve in the black color. So if we see the sine, which is this is a 1 period, right? If I draw this sine in black color, this is a 0 to pi. That's already 1 period, which is -3 sine 2x. Yeah. And let's see in this for this 1 period, and we can sketch the -3 cosecant 2x using that reciprocal property, and we did analysis just now, right? So we have this, and when the sine is positive, the reciprocal of sine curve will have this behavior. So yeah, this is for the whole 1 period. But whenever the sine function has a 0 value and the cosecant function has a vertical asymptote. So we can see this is 1 period. But if you want to draw 2 periods, then let's continue. Yeah, of course, we have this, all this vertical asymptote will happen, right? This, and let's draw 1 more period of sine function. So just go from here, another period. Yeah, so another period of the sine function. You see, for this, 0 to pi is 1 period. From pi to 2 pi, that's another period. Another period of sine function will help us to sketch another period of this cosecant function. So let's have another period of cosecant. Yeah. So now you see the picture. The red is 1 period, the pink is another period. So we see a total of 2 periods of the -3 cosecant 2x. The function now it's 2 periods. Is shown here. So, okay, so now you got the idea of how to graph the cosecant function and the variations of the cosecant function, or the secant function and variations of secant function, right? The method would be very similar, either based on the sine or cosine curve. So to summarize, on how to graph the variations of a secant or cosecant, so I want to give so the summary is as illustrated by the graphing process. That is, if you graph based on which function you're looking at, suppose you eventually want to get a graph of secant, then try to sketch the graph of cosine. Yeah, so suppose I have, my goal is to graph the 5 secant, like 4x, for example, then we can do a sketch of 5 cosine 4x. So once you get this one function, then using the method we talked earlier, then we can get the 5 secant 4x. So if you want to find the graph of 6 cosecant, for example, this function, and you can try to graph the sine function first. And once you get graph of the sine function, then you can easily get graph of the cosecant. Yeah, make use of the reciprocal properties between cosecant and sine, or the reciprocal property of secant and cosine. Okay, that's the method, and by using the properties you learned before, and that can help us to quickly get a good sketch of these functions.